Hello, everyone. We're going to continue with section 11.4 on colligative properties. The learning objectives for this video describe the effect of solute concentration on various solution properties, vapor pressure, boiling point, freezing point, um, and that's kind of what we'll look at here. We will probably talk about distillation a little bit. I'm not going to carry that you memorize all of those details. We'll also probably skip over the calculations for colligative properties. I more care about that you know what they are qualitatively. At this point, I believe you could do those calculations if you needed to, based on your ability to do all the other calculations we've talked about in this course. So let's talk about what we mean. Actually, before we move on, this is not going to be the last video here. You'll notice I left out osmotic pressure. We'll be discussing that in a later video. So let's talk about colligative properties a little bit. It turns out that the properties of a solution are not identical to the properties of the solute, which is not unexpected, right? Because we've been talking about gases dissolved in liquids. They're also not identical to the properties of the solvent. When you put things in them, they're not the same thing anymore. And it turns out that there are many properties that depend only on the number of particles that you have, not on the identity of those particles. We call those type of properties colligative properties. So the idea here, colligative, means of the collection, the things that are a part of that solution lead to it having the properties that it does, not what those things are. So we can look at I should say the solvent properties. It will depend on the properties of the solvent, but it is not dependent on the properties of the solute. It's just how many of them that you have. So let's look at how we can talk about these ideas. So again, the molality, mole fraction are how we are often going to be keeping track of these things. So that's why those were necessary to introduce those conversions. So the first one we'll talk about is vapor pressure lowering. So it turns out that when you have a solute dissolved in solution, the vapor pressure becomes lower. So the tendency to go from liquid to gas is smaller for the solvent than it would have been otherwise. The reason for this is because the intermolecular forces with the solute are essentially stabilizing that liquid a little bit more than it would have been otherwise. So it is less of a tendency to enter the gas phase. So that's kind of why this happens, and we're kind of showing schematically what that could look like here. So we have pure water, and we have the gas phase, the vapor pressure of that pure water, and then if we have something, a non-volatile solute present, you'll notice we have fewer gas particles there. So we've lowered the vapor pressure by having a solute. Notice that it is a non-volatile solute. If it is a volatile solute, so volatile again meaning it will also, if it's a solute that also has a significant vapor pressure, then this doesn't work very well. We have to think about, well, how do those things affect each other? How do those the tendency of both of them to want to become vapors, to enter the gas phase, how do those interact? So this does not always work, but it does work for non-volatile solutes. So this relationship is called Raoult's law, and it says the partial pressure exerted by any component of an ideal solution is equal to the vapor pressure of the pure components multiplied by its mole fraction in the solution. So essentially, the relationship here is similar to with Henry's law. There's a kind of a linear relationship with the mole fraction. Again, we're not going to get into the details of the calculation here. We've done enough calculations, but what you want to know is that when you have a non-volatile solute, it will lower the vapor pressure of the solvent. And then here we're looking at additional calculations that could be done. So don't worry too much about these calculations. That possibly will be homework related to this, but it will not be on the exam. One application of this idea of differences in vapor pressure is laboratory procedure of distillations. So you probably have heard the term distillation at some point in your life. If you take organic chemistry, you will be doing a lot of these. And a distillation is a process where you have a mixture of liquids and you can separate them because they will have differences in their vapor pressure, and you can selectively get the liquid with the higher vapor pressure compared to the one with the lower vapor pressure. Distillation is used in processing many carbon-based fuels. So the crude oil is separated in these large columns into different types of substances that are used as different types of fuel. So gasoline versus kerosene, diesel, other things, and then the difference here is basically related to their boiling points. So you get higher boiling things at the top, lower boiling things at the bottom. And none of these are actually pure, necessarily 100% pure. So gasoline is not a pure substance. It's a mixture of a variety of things that have a similar boiling point. Another colligative property is boiling point elevation. When you have something present in the solvent, again, it is making the solvent more stable, and so the boiling point goes up. Okay, so this is called boiling point elevation. This is the equation that is used to find boiling point elevation. So the delta T sub B, the change in the boiling point, is equal to a constant times the molality. Okay, we're using molality here because we're obviously looking at a change in temperature, so we have to have a measure of concentration that is independent of temperature. So we don't have a volume-based measure of concentration here. That's why we use molality. This constant is a constant of the solvent. It is not related to the identity of the solvent. Of the solute, only of the solvent. So we're showing here some values for this. So for a particular solvent, you could do a calculation related to that. So boiling point elevation is a colligative property. And it depends on the number of particles. That is all that it will depend on, not what those particles are. There's an example of a calculation here. Again, I'm focusing here more on the qualitative aspect than anything else. And we'll see why that becomes important here in a minute. The next one is called freezing point depression. So this is kind of the opposite of boiling point elevation. If you have more of the solute present, it will lower the freezing point for the solvent. So, and this is also related to making the solvent phase a little bit more stable. Your book uses the example of de-icing. Here we live in a part of the country where that is not a thing we have to worry about very much. But this is the equation. You'll notice it's very similar to the equation that was used for boiling point elevation. We have a different constant here than we had before. We are still using molality. and this delta T is how much lower than the freezing point as opposed to how much higher than the boiling point. So it's a similar form, but realize we're going in opposite directions. Some applications here related to de-icing. One application we can talk about that you would be familiar with, more from the boiling point elevation aspect, but it also plays a role in freezing point depression, is your engine coolant. And we did an example of that using in the previous video in terms of doing a calculation. And I said, well, we'll talk later about why ethylene glycol is important. So your engine coolant is important because if you had just water in there and you didn't have the extra coolant, it's possible that it would boil. And if it boils, it would cause damage to your engine. So it's raising the boiling point. It's also lowering the freezing point. So not important where we live, but it's actually doing both of those at the same time. And this phase diagram is showing what is going on when we have a solution versus what would be going on if we had a pure substance. Essentially, what we're doing is we are increasing the range of the liquid phase. So we're showing inside here, the inside purple line is the pure substance range for the liquid. And on the outside, we're showing, okay, well, if we have a certain amount of a solute present, we're going to change that, these numbers. So we're going to, change that freezing point. It's going to be a bit lower. We're going to change that boiling point. It's going to be a bit higher. And so we're increasing the range of the liquid phase, which is what you want for your engine coolant. You want a larger range over which you have a liquid. So that's a little bit about those. I did want to we'll have a separate video on osmosis, and so I want to skip through that, but there's one more thing I did want to talk about and in this video, and that is the colligative properties of electrolytes. So remember, when we are doing these calculations or even just determining relative values, it's based on the number of particles you have in solution. Well, that might vary depending on what kind of particle you have. So if you have an ionic compound, when that ionic compound dissolves, remember, it is going to break apart, right, into pieces. So you don't have sodium chloride molecules, you have sodium ions and chloride ions. Likewise, if you have some molecules, they will break apart, like hydrochloric acid will have chloride ions and hydronium ions. So if you have that, you actually have a higher effective molality than you would if you had the same amount of a molecule. So if this were, say, sugar versus salt, well, the sugar would do a better job per mole of sugar than per mole of salt, because the salt is doing twice the work by breaking apart. So this is something we have to incorporate as we look at colligative properties, is in the electrolyte properties that show up as well. The technical term for what we're doing here is called the Van't-Hoff factor. It's the ratio of solute particles to the formula unit that is dissolved. So for the case of sodium chloride, you have one formula unit and you have two particles per formula unit. So you would have basically 2 divided by 1, so you'd have a Van't-Hoff factor of 2 in that case. Turns out these are not always exactly correct, but you can see kind of they do get pretty close in many situations. So for this class, we want to mainly know how to figure this out. Don't worry about the measured versus predicted, but you can see what you can see here. What I would like you to be able to do is see how we get the predicted number from the formula unit. So we have a non-electrolyte is just always going to be a 1, whereas electrolytes will usually be at least a 2, assuming it's a strong electrolyte. We're not going to get into weak electrolytes here for this kind of a calculation. But then sometimes you might have, okay, you actually have three different particles here, 2 of one type, 1 of another type. So you have 3 and then even 4 in some cases. So you want to be able to figure out this based on the formula. And then from there, look at how that would affect the boiling point or freezing point of a solution. So again, we're doing this more qualitatively than quantitatively, but it doesn't mean there's still a lot to think about, right, in terms of understanding that. There's some discussion here a little bit about why that's different. We're not going to get too much into that. So that is it for this section, or I'm sorry, for this video. There's a little bit more in the section, so please come back and watch to finish out this section and this module.